We are seeing a distinct shift in the enterprise toward autonomous agents. Unlike passive assistants, these systems are designed to hold credentials and independently execute actions across production networks. Most security controls for these interactions rely on a probabilistic LLM as a judge, inference cost of every request. More importantly, it is structurally incapable of producing a reproducible audit trail. A model's judgment can fluctuate between identical prompts. Securing an agent requires intercepting traffic before it reaches inference. This necessitates deterministic pre-inference rejection at the network perimeter, typically implemented via a reverse proxy. At this scale, securing an autonomous agent stops being a prompt engineering exercise and starts being a network engineering requirement. The human is kind proxy sits within a customer VPC as an OpenAI-compatible sidecar. For the agent, only the base URL changes. Specific tenant and user headers drive policy scoping, mapping every request to a stable agent identity rather than a generic process. While deterministic middleware provides the necessary governance at the perimeter, integrating it into complex agentic workflows introduces three specific engineering vulnerabilities. When developers apply human-facing security logic to these autonomous architectures, they create the conditions for payload bypasses and infinite logic loops. This is how a standard reverse proxy evaluates a payload. It walks the messages array backwards and analyzes only the final user message. For a chatbot, this is sufficient. The user message is the only attack surface, so everything else is forwarded unexamined. For an autonomous agent, the threat model is different. The primary risk is indirect injection hidden inside fetched documents. This untrusted data arrives with the tool role. Because it isn't tagged as user, it bypasses the scan and reaches the model context. The fix requires explicit screening. Untrusted content must be routed through an input gate, like KMIR, before it is appended to the agent's message array. In an agentic architecture, data must be screened at the ingestion boundary, not the inference boundary. The second critical oversight is error handling. Most HTTP clients automatically retry non-2xx status codes. If an agent's prompt violates policy, the proxy returns a 403. The standard wrapper immediately retries, hammering the gate with the same payload. This behavior burns rate limits and fills the audit log with thousands of identical violations, making it impossible to distinguish a bug from an attack. Developers must treat a 403 from a security sidecar as a control flow signal, a message that the policy forbade the action, not a transport failure. The required engineering pattern is to hard code a low limit on consecutive blocks before the agent is forced to halt and escalate to a human. If an agent cannot proceed within the bounds of the established policy, it should stop and surface the decision rather than iterating blindly. When an agent hits a block, it may attempt a reflection step, trying to improve its prompt to bypass the refusal. A common mistake is to pass the blocked, violating content back into the context window to explain to the agent why the last step failed. If the block was triggered by an injected instruction, reinserting it for an explanation gives the payload a second delivery path directly into the agent's reasoning loop. To prevent this, never echo blocked content back into the context window. Provide the violation reason, but keep the triggering payload outside the agent's memory. Security in a multi-agent system requires absolute state separation between the refusal signal and the data that triggered it. The fourth architectural weakness involves incremental delivery. In standard streaming, tokens are sent to the client as they are generated, before the final output evaluation is complete. In a chat interface, a human might see a few words flicker before the stream is cut by a security gate. But agents do not wait for the end of a sentence. An agent can parse partial tokens into a tool call and execute it in milliseconds. By the time the proxy cuts the stream, the action is already dispatched. For internal reasoning calls, agents must be configured with streaming disabled. This ensures the output gate finishes its evaluation before any bytes reach the agent's parser. Speed is a liability if the agent's execution outpaces the perimeter's ability to evaluate the payload. Why go to these lengths for a deterministic architecture, instead of simply asking a second LLM to monitor the first? This view of the European Parliament Assembly Hall reflects the growing regulatory pressure. Under frameworks like the EU AI Act, companies now face strict transparency duties for autonomous decisions. Regulators and enterprise buyers no longer accept probabilistic dashboards. They require specific, reproducible evidence of what happened during an interaction. This performance summary demonstrates why a deterministic proxy is superior. By making 0 external calls and blocking over 2,000 payloads before inference, the system enforces policy without model drift or vendor telemetry. This architecture actually lowers operating costs by stopping adversarial payloads before they can consume model tokens. For every decision, the proxy generates a receipt ID and a chain tip, creating a cryptographically anchored record of the enforcement action. Hick's write-ahead log ensures this evidence is committed to disk before the response is even sent to the agent, creating a tamper-evident audit trail. By treating security as a component of control flow, we elevate AI governance from subjective, probabilistic advice to a verifiable technical audit trail.